Hey there and welcome to another LeetCode problem. So today we're going to be doing problem number 1230, toss strange coins. It's going to be the premium problem of the week for the first week of June. So you have a bunch of coins and the ith coin has a probability prob I of facing heads when tossed. Return the probability that the number of coins facing heads equals target if you toss every coin exactly once. So we go through this probability array. And this is the probability of getting a heads. We toss every coin once, and then basically what they're saying is what is the probability of our total number of heads equals the target. And so what we can do is we can actually draw let's draw a decision tree. Okay. And so what we're gonna have to do is instead of drawing a decision tree, let's do something else. So let's think of how we would figure out how many, what's the probability of getting a heads, what's the probability of getting a tails, how does that even work? And let's just use something like, instead of drawing a decision tree, let's just have an array of maybe 2 elements. So let's say 1 is 0.4, second one's 0.2. And we're trying to figure out what's the probability of getting, let's just say, some target like 1, right? Well, what we need to do is we need to ask ourselves, so the way probability works, for the total probability, the probability of every single event, right, is P of 1 times A1 plus P2A2 and so on, where probability is the probability of that event, and then A is the event, whatever that's worth, equals the total probability. So this is P total. Okay, and knowing this, we can figure out what are the total ways we can get 1 in this case. Like, what are the different ways we can get 1? So the different ways we can get 1 is we can get a 1 and we can get a 0, right? Or we can get a 0 and we can get a 1. And so the probability of either of these things is just P of this happening plus P of this happening. And from this, we know that what's everything that can happen? Well, the other thing that can happen is 0, 0. We can also get 1, 1, right? So I think that's every case. Yeah, and so you would know that the probability of all of these things has to add up to 1. Okay? And then, so P of all this has to equal 1. Because the probability of every single event has to equal 1. So now we can simply figure out, how do we figure out what things have to happen for this to be 1? And then like what is our base case and things like that. And so for this simple example, let's just say, like I said, it has to be these two things for this example, right? It either has to be 1 and 0 or 0 and 1. And so let's think how that can happen. And then we can think of just a general problem we can have and then when to break out of it and what's a base case. So for this 1, 0, we'd have to roll a 1, which would be 0.4, right? And then for the second one, we'd have to roll a 0. Well, or flip a 0. Well, what's the chance of getting a 0? Well, the chance of getting a 0 is 1 minus this, right? Because you either get a 1 or a 0, so the chance of getting a 1 is 0.2. Then the chance of getting a 0 is 0.8, and that's also due to this thing, right? So the probability of every single event happening together is the total probability. So the events you can have is and by the way, this P total should equal 1, right? As I said here. And so yeah, the probability of let's say tails or whatever it is, it's going to be 0.8 here. So that's the probability of the first event. Now the probability of the second event is this, 0, 1, and the order does matter because the probabilities don't have to be, they can be different in the array. If they were both 0.4, it wouldn't matter, but if they're flipped now, it matters. Okay, so now we have to get a 0. So to get a 0, it's going to be 1 minus 0.4, which is 0.6. And then we have to get a 1, which is 0.2. And so we would just add these up, right? So this is 0.32, and this is 0.12. We would add that up. So, yeah, so this plus is actually for these two. So when we add these up, we get 0.44. So there we go. And so the probability of getting a 1 here is 0.44. And similarly for the easy example of the probability of 4 here is just 0.4 because we only have 1 coin. Now the probability here for target equals 0, we can also do this as well. This is a pretty simple example to go through because there's only one case that this can actually happen for, right? So the probability of this happening, if the probability of tails is 0.5 and we have to get 0 heads, it means we have to get a tails every time. And so that would just be 0.5 times however many things are in here. So 5. And I'm not going to do the math there, but that should be this right here. So now let's just think of the general case of how do we actually calculate? Like it's easy for a few, but what if we, have a bunch, like 1,000 numbers and we want the number 5? They're just, the possibilities are going to be so big, we can't really count those up. But what we could do is we can take the probabilities we care about and discard the rest. And so for something like a base case, so for one thing, let's just say we do this. So we're at some index, call it I, right? We're at some index and then we have a target. So what we could actually do is we can say P at that index. So remember, you can have two different things happen. You can have a heads and a tails, but we might reach our target in getting either one of those, right? Like let's say our target here is like 3. We can get a heads or a tails in the first one. It doesn't matter, like because then later on we can still succeed. And so if this target is big enough, it doesn't we have to account for both the heads and the tails. And so what we'd actually have to do is the probability of success is going to be P of heads, let's say, right? The probability of heads times, and then we have to give it some recurrence relation saying some other stuff will happen afterwards. So if we get a heads, what happens? Well, the index goes up, but now our target value goes down, right? And then we can also get the probability of tails. So let's just say tails, the index goes up again, right? And by the way, we're getting these probabilities, so we're going to have this array, right, of probabilities, and this I is just the index in the array that we're currently at. So hopefully that makes sense. Okay, so P tails, I plus 1. Now, target is the number of heads we want. So if we got a tails, we still want the same number of heads, right? We didn't get a heads. And now let's just think, okay, so we got this recurrence relation, but how do we actually get base cases? Well, for one thing, we know that if the target is less than 0, that's a base case, right? Like if we had target 0, let's say here, but then we got a heads, then that's no good. So if target is less than 0, we can simply return 0. And then by the way, we can just return 0 for anything that's not matching what we care about. And then we're only gonna add up the probabilities of things we care about, and then that'll give us our actual result. So if target is less than 0, then obviously we want to return 0 because we failed. Now, what are our other base cases? Well, our other base case is when I is a length of whatever array, let's just call it R, we're at, right? When we're at the end of this array, there are no more coins to flip. So when there are no more coins to flip, what's our base case? Well, we want the target to be 0 at that point, right? And so we can just return, check if target is 0. If yes, return. Now, what do we want to return? So actually what you want to return is, if the target is 0, you want to return 1 because we succeeded. And then we're going to multiply all these numbers times 1 because we succeeded. And then if the target is not 0, then we want to return 0 because that output we don't care about. So hopefully that makes sense. This is kind of similar to, I think, I did have something else with probabilities. I forgot if it was Stone Game or 21 Game or something like that. But that's kind of the same thing. For all these probability things, you want a base case of 0 when you have an output that you don't want, and then you want a base case of 1 when you reach an output that you do want, and then you're just going to multiply a bunch of numbers beforehand by that 1 to get the actual probability of getting this 1. So you're going to have some P's, this recurrence relation, you're going to have a bunch. And so just to go through like a quick example of what that would look like, let's say we have probabilities, let's just say we have a half, right? So a half, and let's just see what that would look like. Let's just say we have, I don't want to do too many. Let's say we have 3 halves. So the probability of everything's a half and our target is 2. So what would this look like? Okay. So once again, our probability, so we'd go into our first, let's just call it DP, right? We'd have index 0, we'd have target 2. Now let's just say R is our result equals, so remember probability of heads times index plus 1, and then heads we got target minus 1. So let's just say this starts at 2. So now this would be 1 plus probability of tails, because we can still succeed if we get a tails. So in tails index 1, same thing, now target's 2. Now we recurse, so let's just recurse into this one. And so what's dp of 1, 1 here? And we are going to have a visited as usual to make sure we don't do repeated work. So dp of 1, 1, same thing we're going to have. Let's just make this bigger. We're going to have a result, right? Equals. So what are the things we care about now? Okay, well, we can get a heads. So this would be index 2. Now our target would be 0. Or we can get a tails. Now it would be 2 as well, but our target would still be let's see here. Yeah, our target would be 1 here. Okay. So now, what's dp of 2, 0? So this is going to get a little big, but that's okay. So dp of 2, 0. Let's just say that. By the way, our final index here is 2. Yeah, okay, sure. 2, 0 is going to be same thing, right? So res is going to be 0.5. So I'm not going to include this 0.5 times head. Well, actually, I'll include sure. 0.5 times heads. So now the index would be 3. Now this would be -1. So now we know that when we hit this -1, our base case is going to return 0. So this can cancel out. And then our other case is dp of, and that would be 3, and that would stay 0 if we get a tails, right? So heads, heads, tails is what we'd have, and that would be a successful solution. Okay, so now we know that this is going to be 1. And so this is going to be 0.5 times 1. So this is going to return 0.5. Okay, so this right here is 0.5 times 0.5. Okay, now this 2, 1, I don't think we ever did yet. So what's dp of 2, 1? Okay, remember we have to have a res again. Equals 0.5 times, so we go to index 3. 0 plus 0.5, index 3, 1. Now we know that index 3 is the length of p, so we know that whenever we reach the end and our target is not 0, that's going to give us 0, right? So this is going to be 0. This is going to be 0.5, so that's going to return 0.5 up here. Okay. And so you kind of get the picture of how this goes. Like we're just going to be recursing down and getting these base cases, and then we're going to be returning up. And then we'll have some final output in the end. You can draw it out if you want, like the whole thing, but I'm going to stop here. And we are going to be doing repeated work because we can easily get to the same place twice. For example, we can get a heads and a tails, or a tails and a heads. And then when we're at this situation, we'll have the exact same thing, right? We'll have index 2, and then our target will be 1. And so we do want to have that visited array or set. So hopefully that makes sense to you how this is going to work. And so let's code it up. The code is actually pretty straightforward. So we have our visited set. And yeah, once you do enough of these DPs, like you learn to recognize things are DPs. And also I do find that memoization solutions are much easier. And then if you want to get practice with bottom up, I'd encourage you to do that as well. You should be able to get a bottom up for this. Okay, so we have an index, we have target. So remember our base cases. So if target is less than 0, we can return 0. And then if index equals length of probability, that means we have no more coins, and we just return target equals 0, right? So if the target is 0, then we want to return 1. Otherwise, we didn't get our solution. Then our third base case is, as usual, is if index target in visited, return visited index target. Okay, and now, like I said, we are just going to take the probability of heads and tails. So that's going to be prob index times, and so this DP is going to be index plus 1, and since we got a heads, it's going to be target minus 1. So that's one case, and then we do the same thing for tails, right? So prob index, and remember that this prob index needs to be 1 minus prob index because this is the probability of tails. Right, so that's the probability of tails, and then same thing times dp index plus 1. Now it's not target minus 1 because we got a head, so it's the same thing. Okay. Should match, I think. Maybe I need another something. No, actually, no. Okay. So that's going to be that. Then we just return, right? Return. Standard DP, like half of this code is just vanilla memoization. So, okay, and then we just do a simple return DP 0, and then our target is our initial target. Try that code. What do we got? Index, invalid syntax. Right. Cool. All right. And so let's think about the time and space complexity here. Okay, so how many different states can we have? And how many different targets can we have? So I think technically we can have, I think technically, now what we could do if we wanted to is we could return early. That might be a slight optimization if you wanted to make that. And that would look like at every single point, we just check what's our target and how many elements do we have left. And if we can't, like, let's say we would just do something like length list minus whatever index we were at. And that would give us like the number of possible heads we would get. So let's say, you know, we had something like, just say we had some numbers, whatever. These don't really matter. So 0.2, 0.2, 0.2, whatever. And let's say our target is just like 5, right? We could literally start here and we could say, okay, what's the total possible number of heads we can get until we're at the end at whatever index? So that'd be 3. Then we could say if our target is greater than that, we could just return immediately. We can just return 0 immediately. So that would be a slight optimization if you wanted to make that. I think like time and space complexity would be the same, but your code might run a little faster. Okay, so anyway, so I think the time or the possible states we can actually have here is we can have every single index. So it's going to be, let's just say index, and then we can have every single target as well, right? Because we can technically just get tails over and over and over and over. So we can have every value of every tails and every index. So that's that. Space. It's going to be the same thing. We need to be storing every single index and every single target, technically. So that's going to be that, I believe. Yeah, and that's going to be it for this problem. So if you like this video, please like and subscribe, and that really helps grow the channel, and I'll see you in the next one.